Okay, so welcome everyone to the last Topos Institute Colloquium of the year. So thanks to all of our attendees on Zoom and on the YouTube live stream who have stuck with us at the end of the year here. We're really grateful for that. And as a reminder, the colloquium will restart again in early February next year. So I hope you'll be back for that. So with that, we're very fortunate today to have Andrei Rodin, who will be telling us about Univalent Foundations in Applied Mathematics. Andrei, please.
Okay, thank you, Evan. And hello, everybody, and thank you very much for having me here. So I will talk about Univalent Foundation and Applied Mathematics. So what is the aim of the talk? I want to actually present and popularize a little known part of Vladimir Voevodsky work, which did not bring published results despite of significant efforts contributed by Vladimir to this project. And by Vladimir's own judgment, in his interview of 2012, he, according to him, he wrongly defined some of his research priorities in this project and had to abandon it. But he hoped to come back to the project later in his life and career. But unfortunately, Vladimir's premature death in 2017 did not allow him to realize this plan. So I shall try to convince you that the project is actually promising, important, and worth to be pursued further. In this talk, I try to interpret and develop some of Vladimir's ideas very modestly, ideas. Actually, I take this mostly speculative parts of his ideas rather than technical work that he judged himself useless and without claiming, of course, any accomplished result here. So Vladimir is known actually for two major contributions. First is, of course, algebraic geometry, and second, foundation of mathematics. But he also spent important part of his time and effort working on applied mathematics, more specifically in the mathematical biology, and that's this unfinished project that I made. Okay, now I'm going just to quote some things from Vladimir. So that's his interview to his friend Roman Mikhailov. It's on internet in Russian, so that's all my own translation. So it's a big interview in two parts, and so in this part he just makes some narrative about his career, Vladimir. So he says, since fall 1997, and that's 5 years earlier than he received Fields Medal, he says, I realized that my main contribution into motif theory and the motif cohomology was already accomplished. Since then, I was very consciously and actively looking for a theme to work on. Considering tendencies of development of mathematics as a science, I realized that mathematics is at the age of crisis, or more precisely, two crises. The first crisis concerns the gap between pure and applied mathematics. And that's exactly the topic of my talk today. It is clear that sooner or later, there will arise the question of why the society should pay money to people who occupy themselves with things having no practical application. The second crisis, which is less evident, concerns the fact that mathematics becomes very complex. As a consequence, once again, sooner or later, mathematical papers will become too difficult for a detailed checking, and there will begin the process of accumulation of errors. Okay, so the second project, of course, became Univalent Foundation of Mathematics, and the first one that we had, I will discuss more details. So he says, I decided to do something in order to prevent this crisis. In the first case, that meant to find an applied task, which would require for its solution methods of pure mathematics developed during the last years, or at least during the last decades. I was looking for open problems which would be interesting for me, which I could where I could apply today's mathematics. Finally, I chose, as I now understand wrongly, the problem of reconstruction of history of populations meaning populations of living organisms, including humans, on the basis of their present genetic constitution. I worked on this problem about 2 years and finally realized in 2009 that everything that I invented was useless. Actually, as I checked in archive, which is, by the way, very well accessible now due to Dan Grayson on the site of Institute of Advanced Studies. Actually, he started earlier than 2007, so it was at least 5 years, but probably most actively he worked this last year. So I made, I'm sorry, it's kind of messy, it's kind of timeline. So green is his work in algebraic geometry. He also more or less stopped in 2010. Then, of course, foundation of mathematics, foundations and verification, that's started about 2005 or 2006, and that's work on population dynamics was something between 2004 and 2009. So you see the beginning on work on foundations more or less coincides. No, actually, active work on foundations coincides with the abandoning. He started earlier with abandoning this work in applied mathematics. Okay, and now I also quote from earlier sources, actually two public lectures he gave after receiving field medal. He traveled to China, where he actually received the medal, right? And then also to India after that. And so that was lecture in Wuhan University in December 2003. And titled, "What is the most important for mathematics in the near future?" So I just now present just summary of these two lectures, and then I come to discussion. So he says there are two most urgent needs in today's mathematics. No, something he repeated in this interview we just seen. To build computerized library of mathematical knowledge, so a computerized version of Bourbaki's elements. And second, to bridge pure and applied mathematics. So here he makes remark about first, probably I skip it. So this second remark is relevant. So he says, we discovered very fundamental classes of new objects, including categories, sheaves, cohomologies, simplicial sets. They may turn out to be as important in size as algebraic groups, but presently we don't use them for solving problems outside the pure mathematics. So one reason for that can be sociological. Only few people have a profound knowledge both of modern mathematics and of some other research field where an application of modern mathematics can be possible. Another reason concerns the current scientific policies. In order to apply abstract mathematical theory to a concrete practical problem, one needs, first of all, to generalize this problem and abstract away the intuition associated with this problem. But the current finding policies favor rather fast solution of concrete practical problems, kind of $1 billion drug. In order to apply mathematics to a given problem outside mathematics, one should begin with the opposite move. Instead of trying to concentrate on future applications of mathematical theory to the real life, one should abstract yourself from the real life and look at the given problem as a formal game or puzzle. This is a reason why new mathematics too often strikes one wrongly as what moves away from real-world problems. So the only reasonable policy in mathematical research and in science in general is to support one's curiosity and one's sense of beauty in science. So you see, it's kind of complicated because on the one hand, he wants mathematics to be applied, definitely, right? But on the other hand, he also defends, of course, kind of pure mathematics. But in his thinking, that's actually two sides of the same model. So this pure mathematics does not generally, or should not rather, prevent applications, rather the other way around. Right, and then he introduces actually what he calls layers of today's mathematics. So he distinguishes elementary mathematics, like Pythagoras theorem, higher, so-called higher mathematics, like integral differential calculus, so-called modern mathematics, like modern algebra, basic topology logic, and set theory. This is his examples. And actually he adds, that's probably his invention in a sense, what he calls synthetic mathematics. So that's kind of more recent mathematics that he actually is engaged himself at the point, like representation theory, algebraic geometry, homotopy theory, in particular motivic homotopy theory, differential topology. So he separates these mathematics as something separate from just modern mathematics, and modern begins in the mid-19th century, according to this account. And then he says elementary mathematics is integrated in the everyday life, like logistic. Higher is integrated in most sciences. Modern mathematics is integrated into some sciences, like group theory and quantum mechanics. And synthetic mathematics is very poorly integrated, if at all. And so I just comment here that this kind of partitioning of, I'm sorry, it's actually very much resembles what back then in Soviet Union we had very standard account given by Kolmogorov, actually, except this last one that Vladimir added up, but interesting that that was kind of historical stages, right? And that was used by historians, and that's, I think, very interesting view on mathematics that I didn't see often elsewhere, right? He thinks about these historical layers as coexisting, not as just kind of development, and one stage of development succeeds another one, but he just has this perspective that all these coexist, which is, I think, sociologically true, of course. It makes me think, actually, it is not my original metaphor. I actually forgot the quote, but there was another author who already compared kind of architecture of mathematics with the city. But here is something, I think, new, because typical, at least here in Europe, typical city comprises houses and the infrastructures built in very different times. Say 3-5 centuries, typically for France at least, and they all work together somehow. They all fit together. They should. So that's how Vladimir sees mathematics. And then he actually observes that this new level is very badly integrated, as he says, right? So he wants mathematics to be integrated in society, connected to other sciences, applied in some very so sense, that that's really his concern. Yeah, I just remarked that he actually presented again this picture in his 2014 Paul Bernays lectures in Zurich. Okay, but I will not talk specifically about it. Yeah, so it's Vladimir once again. Sometimes I paraphrase because I made this text on the basis of his slides. No recordings was available, so sometimes I paraphrase, sometimes it's a precise quote. Mathematics is an integral, albeit very special part of general problem solving activity, which by itself is a pre-scientific human condition. That's I say pre-scientific human condition. He didn't use this word. Various practical problems which are conceptualized and approached with the common also known as conventional thinking, are more effectively solved via mathematical modeling or applied mathematics. He equates these things, which in its turn give rise to the pure mathematics. The pure mathematics grows with solving such external problems, which come via the mathematical modeling, and so with formulating and solving its own internal problems in the form of proving mathematical conjecture. And then he makes this diagram that I put in LaTeX. So we have this conventional thinking, meaning just kind of life with a lot of practical problems, right? And then there is mathematical modeling as a way of solving this problem. And finally, there is a pure mathematics, which actually has kind of internal problems, right? Proving conjectures. And then there are these two important channels from modeling to pure math, or if you like, from applied math to pure math and back, which he discussed later. So he says, over the last few decades, the situation, as described above, was getting more and more out of balance. Arrows 1 and 2 at the diagram, which connect pure and applied mathematics, were weakening. A weak incoming flow of external problem restrains the internal development of pure mathematics. A weak outgoing flow of useful solutions restrains the support of mathematics provided by the society. Breakdown arrow 2, it means from pure mathematics to applied mathematics, eventually means no salary for mathematicians. I don't know if it's relevant, but that's true that the late 90s in Russia, that was very, very, pertinent issue, right? Why any scientists should be paid, many scientists were not paid at all. Of course, after, it's a little bit ironic that Vladimir says all that after receiving Fields Medal that surely somehow assured his academic career after that. But I think he never came out of this concern, right? That was when he had no particular status, even in the university, and that was something that he was thinking about. So breakdown of arrow 1, it's from applied mathematics to pure, eventually means no new ideas in mathematics. That's rather strong claim. So according to his view, mathematics does not have a potential for this purely internal development. So it's always need these problems from outside to be solved, otherwise it stagnates and just somehow ceases to be. All right. Now he thinks how to improve it, right? How to improve this challenge. And here it starts becoming particularly interesting, what he's saying, because after that, what I presented so far, I think it's a reasonable view, but it's hardly original something, right? But here he has, I think, very interesting ideas of how to make this, to clean these channels, so to speak. So his key idea here, it's change the existing pattern of using computer technologies in the general problem solving. And so he says kind of existing pattern is the following. So we have all that practical problems that he calls conventional thinking, right? We have computer modeling that already showed, and we have mathematical modeling in pure math. Okay, that's a general scheme. But then the flow of problems down to the mathematical modeling layer is filtered through the computer modeling layer. So that means that that all mathematics which is applicable should be somehow applied in computer modeling. So if you have piece of mathematics that we cannot put on computer in one then to the other, it's somehow hopeless to apply it. That's as I understand it. Okay, as a result, the mathematical modeling layer and as a consequence also the pure mathematics layer receive less problems than they used to receive before the rise of computer technology. That's something interesting. So in a sense, computer technology prevents, no, at least at that point, right, in this part of the whole mechanism, computer technologies actually prevent kind of faster development, or at least they make this flow between applied and pure more complicated and somehow slower. This particularly, says Vladimir, affects today's abstract mathematics. problems which pass through the filter are formulated in the old style language of variables and analytic functions, while the language of today's abstract mathematics is the set theory. Right, that's also important to have in mind that that was all before univalent foundations, right? So he still believes in set theory, that this set theory is a foundation of this most recent mathematics that he calls synthetic. Right. Yeah, that just remark to this. Here the years actually explicitly he first mentioned univalent foundations and invented the name. The name, by the way, univalent came from double translation back. It was a book translated to Russian on category theory, where faithful functor was translated as univalent in Russian functor. And so he took this name back, univalent, and introduced it into English in a different sense, of course. Right, so that was 2010, and but there was also interesting talk in Institute of Advanced Studies in March 2006, where he somehow it's called Foundational Mathematics and Homotopy Theory. So he had already some ideas that homotopy theory could play a role in foundations, but still it was not accomplished even as an idea, and that came late in 2010. But still in 2009, Vladimir still explored this idea of using set theory as a link between pure and applied mathematics in his unpublished manuscript called Singletons. I'll come to that just in a minute. Okay, so here is what he calls the double translation of problems. That's the same point he just explained, just a little bit more elaborated. So we have this computer model, right? Then we have this outside world, or how he called it, conventional thinking. But important, there is this computer model, and typically it implements kind of 19th century style analytic language of mathematical models, right? And then, of course, these models could be recasted in set theoretic language. But here, what he calls double translation, right? So he wants kind of more direct error not existed basically here, because it's probably not commutative diagram, that would connect more directly foundation of modern mathematics with computer model without passing via this 19th century language. Okay, so that's what he wants to achieve. Computer model, set theoretic model directly, and then it sometimes could become also analytic model in the 19th century style. Okay, I just try to give example to what he, to explain myself and now to you by an example. So take like climate research, right? That use a lot of computational models, of course. And so I am not an expert, but what I try to check is that at least a major part of these models are based on Navier-Stokes equation. Okay, and then there are a lot of more recently invented smart algorithms that compute solutions of these equations. Okay, and so new mathematics here involved only on the level of these algorithms. So the mathematical foundation of the model, right, remains Navier-Stokes equation, and the Navier-Stokes equation is a 19th century style thing, and it's actually something more than a style, right? It's a really 19th century concept. It's very powerful, of course. But say if we translate now, as we can do, of course, Navier-Stokes equation into language set theory, but then we come to this double translation, so it doesn't solve the problem, because the problem is to have a more direct access from foundations, and by which Vladimir at that point actually means set theory, to computer, right? To something computable and hence applicable. That's so his project, how to improve on the situation that he finds not satisfactory, is to find this shortcut from foundations to computer. Right, in order to implement that's his words, or his paraphrase words. In order to implement this new scheme, we need in particular to reformulate fundamental and applied scientific theories in the language of today's abstract mathematics. That is the set theoretic language. For this end, we need to specify for each theory a notion of basic unit, right? And then he tries to develop the project, which I think doesn't work and somewhat naive in a sense. So he think, why not how to apply set theory kind of directly, right? For modeling. Let's consider sets where elements are, say, biological individuals, or say particular persons, or in financial mathematics, we can think sets of companies, or in political science, set of waters, or set of particles, genes, molecules, etc. Why not? And then we may so interpret set theory, right? And then develop like nice mathematical theories on the basis of that theory. And then why this mathematics wouldn't apply back, right, to individuals, companies, to molecules, whatever. Yeah, so he concludes this lecture saying the most important task for mathematicians to produce examples that demonstrate the effectiveness. So he tried to produce an example, as I just mentioned. He didn't achieve it, and there are some papers I don't take now into consideration. He tried to develop some sort of categorical version of probability theory for that reason, also some kind of special set theory, but apparently that nothing of this really worked. And I just tried to introduce a little bit of context around this idea to use set theory in this applied way, right? And so my first quote would be from Marshall Stone. It's actually, he made it from a paper that defends this new mathematics. And new mathematics, probably not everybody knows, that's a project of educational reform of the United States of school mathematics, by the way, motivated by Soviet Sputnik in 57. Right. And so it was kind of set-based Bourbaki style things which you can still see in France. Even a lot of it was also so it started, was rather active, but then very soon abandoned. And similar things a bit later actually happened in other countries. That's an interesting topic, but we know. So Marshall Stone was one of leaders of these movements, of this reform. And so, among other things, he says, while several important changes have taken place since 1900 in our conceptual mathematics, or in our points of view concerning it, the one which truly involves a revolution in ideas is the discovery that mathematics is entirely independent of the physical world. You see? So one who defends set-based Bourbaki-style mathematics is actually somehow also defends pure mathematics independent of the physical world, right? And that's, of course, in odds with Vladimir view, right? So at least Martin Stone had to believe that mathematics entirely have this internal capacity to develop with an application that's somehow different issue, but mathematics as such does not need it. Okay, and that's so that's a person who really at the same time defends Bourbaki's style even in school mathematics. And as a contrast, I just give words of Vladimir Arnold. And Vladimir Arnold is a very sharp critic of Bourbakism. He kind of hated that's I didn't include here his talks about this, but he is very known for these things. And so he developed kind of very nice, I would call it 19th century, even if it's very modern and really great. I followed his course on differential equations and mechanics, and they're very, very famous and very nice books. They're actually in books. If someone didn't see, I really recommend everyone. So one of his, it's published in 98, but I remember he's saying that's much, much earlier. So he says something like this, that mathematics is a part of physics. Physics is an experimental empirical science, a part of natural science. Mathematics is a part of physics where experiments are cheap. Right. No, I just compare with what I know is a quote from Ernst Cassirer, who defends this, we would say, old-style Kantian view on mathematics, but trying to take into account all later development on Euclidean geometry, everything. And so he said the Kantian principle, according to which mathematical concepts should be sourced in intuition, which is one of tenets, of course, of Kant's view, but he thinks is intuition very broadly. So in Cassirer's view, that means that these mathematical concepts should be sourced in the mathematical physics and should prove effective in this field. So in that sense, I think Vladimir Arnold would agree. Unfortunately, I found this quote already after he died, so I didn't have chance to show him. So Vladimir's attempt to stick to the set theoretic foundation and at the same time promote the kind of unity of mathematics with physics and other natural sciences is very unique, and I think hopeless. That's my judgment. So there are actually some interesting things. Georg Cantor himself considered application of his set theory in biology, but that's at least today looks like historical curiosity. Nothing came out of it. Right then, we may think about attempts to apply this Bourbaki style axiomatic presentation in scientific theories that was promoted by Patrick Suppes back in the early 50s, and then actually it's produced a whole industry of such works. But as far as I know, that at best is interesting for philosophers, right? Who kind of doing this, they can analyze some sort of structure of scientific theories and how one theory relates to another theory. But in my understanding, no really working scientists ever use something similar, right? Knowing the same, that's probably more interesting when we talk about computer science and formal ontologies in computer science. So all this business of presenting stuff with formal ontologies, but again, I don't think it may work in that kind of straightforward manner that just proposed by Voevodsky. So that would hardly help to solve what he calls this double translation problem. Okay, so and here is a quote from Bill Laver from 70, and he said, and so Laver is on the other side of the camp. He's kind of critique of set theory, right? So he says set theory should apply not only to abstract sets divorced from time, space, rings of definition, etc., but also to more general sets, which do in fact develop along such parameters. But by concrete set, he actually means toposes here, right? So basically, his proposal is not to even improve set theory of Zermelo-Fraenkel style, but change it for, say, topos theory, category theory, and interpret this topos theory in kind of close relations to physics. So again, Laver wouldn't be, at least I think he would not be enthusiastic about a project of somehow connecting set theory in its standard form to physics, to something like this. All right. Yeah, and then of course, since we talk about category theory as a alternative foundation mathematics, there is a large body of works aiming at application of category theories in theoretical physics. Laver had some papers, and John Baez, Urs Schreiber, who also presented this seminar, and many other people. But interestingly, that Vladimir actually did not follow this path, but rather looked for application of what he called synthetic mathematics, is more empirically oriented, or I would say data-driven research. And here is a quote from the interview. So he says, science should collect and comprehend a new knowledge. The collection part is very important. There is a view according to which all important observations, so empirical observations, in science are already done. The general world image is clear, so it remains only to arrange this knowledge and pack it into a compact and elegant theory. This view is wrong. It is not only wrong, but also supports a very negative tendency to ignore everything that doesn't fit a ready-made theory or hypothesis. This is one of the most important problems of today's science. So he actually looked at different direction, but still, I think it's interesting, right? That probably he realized that that after all, set theory doesn't work as a good foundation for science. So he became changing his mind about foundation. Sometime, at least in 2006, already had some, at least that paper about homotopy theory and foundation, and in 2010 he changed it completely. In 2009 he abandoned that project. So it's not unprobably. I'm very sorry that I never asked Voevodsky. I had the chance, actually. I spent some time in Princeton Institute by his invitation, but I never asked him about these questions when I had the opportunity to do that, right? Normally, he liked I talked about history of mathematics, about Euclid, Grassmann, and I asked him about mathematics. That's so we missed, very unfortunately. So I have only to conjecture now. So it looks like his changing view on foundations also could have an impact on his view on that applied project. Right. And so, yeah, that's probably the last quote I'm going to use in this talk. So he says, concerning the pure and applied mathematics, I have the following picture. Pure mathematics is working with models of high abstraction and low complexity. Mathematicians call it elegance, low complexity. Applied mathematics is works with more concrete models, but on the higher complexity level. Interesting application of the modern pure mathematics are most likely in the area of high abstraction and high complexity. This area is practically inaccessible today, mostly due to the limitation of human brain. When we learn how to use computers for working with abstract mathematical objects, this problem will be no longer important. An interesting application of ideas of today's abstract mathematics will be found. And next part is actually the only evidence I find that he could still relate this Univalent Foundation project and applied mathematics project. So he says to Roman Mikhailov, it's 2012. That's why I think that my present work on computer languages, which I understand as work Univalent Foundation, couldn't be anything else, best of my knowledge, that allow me to work with such objects, will be also helpful for application of ideas of today's pure mathematics in applied problems. All right. So we can think to solve this double translation problem, not with set theory as he first proposed, right? But by univalent foundation. So we find some kind of direct implementation of, on the basis of univalent foundation of, say, abstract models like sheaves, motifs, or whatnot. So it will be a chance to apply these concepts directly to empirical data and could arise or not arise this analytic model. That's already less important. All right. Yeah, so that's the idea, but then some objections. And one objection is, of course, that the same shortcut can be made with any proof assistant, right? Not why univalent foundations. And that's actually interesting. No, that's probably a topic for different talk and not by myself, but in my understanding, at least what I learned from people like Kevin Bazar, for example, that using type theory in proof assistance with dependent types, of course, became a rather common standard, right? Like in Lean. And but using high identity types, high inductive types, and all the other special features of, say, homotopy type theory didn't. And the current version of Lean uses uniqueness of identity proof axioms. All proofs of given proposition are equal. So that's completely makes, of course, homotopy type theory redundant. And I just looked in the recent paper by Kevin, where it's a paper on formalization of Grothendieck schemes. And then he just makes a remark, univalence, and why it's not helpful. Even it's could be kind of theoretically helpful, but in practice, it turns out that is not. So there is some technical context. I'll not try to reproduce here, but he says univalence does not solve the problem we counted here, right? After the substitution, so the idea, of course, and kind of hope for univalence is that substitution may transport structures in all cases. After the substitution univalent system, we would have a proof of exactness of one diagram, and we want to prove exactness of another diagram, and the diagrams now have the same objects, which is guaranteed by univalence, but not necessarily the same morphism, and that still needs to be verified. Actually, I very much hope to engage people like Kevin or maybe Jeremy Avigat, who actually are rather skeptical about homotopy type theory and prefer to use and develop Lean without it, to somehow give more systematic arguments why. And I try to ask also Jeremy, that's somehow, I think that would be really interesting and useful discussion. But anyway, at least we may say there are some practical difficulties, and Lean actually grows very fastly now, but without homotopy type theory. All right, and then that's not really objection, it's rather kind of remark or observation. That's when I try to figure it out, is there anything around which somehow resembles Vladimir's idea of this kind of direct application say modern mathematics to computer and to data? I somehow fought on topological data analysis, right, where we have a relatively recent theory, persistent homology theory, which actually was developed in different contexts, in context of Morse theory, and but became very useful. So I don't know, I don't have time, but probably if some of you did not see that, the idea is that you have say data with certain metrics. So you need some kind of metric saying these certain two data are closer and or less close to each other. No, of course it can be not just two-dimensional space, but a lot kind of high-dimensional space. And then idea is very easy. So you imagine kind of spherical neighborhoods, right? And then two things, then two neighborhoods intersect. You say these things are connected for, say, 2 points, right? If it goes for 3 points, you say you have a triangle. Right, and the same for all simplexes in all dimensions. And then with some condition, you build a simplicial complex And all that just goes automatically with the algorithms. Such algorithms already well developed. And then, right, the question is how to choose the right distance. And here the trick of persistence comes. So the idea is that you just vary your distance from, say, 0 to maximum continuously. And then you see that certain structures, they are very short-living, right? So you just ignore them, and some others which persist, right? So that's kind of real topology of, which is more than one, so this stability areas, of course, could be many. But anyway, so that's the way to how say, prescribe certain topological structure to a big sets of data. And again, I try to look literature. I don't think that there is any, how to say, shared opinion of what it really reflects. But in many cases, it's really helpful. It helps doctors, for example, right, to see kind of similarities and things. And there are even more serious attempts, say, in neurobiology, because there people say when they study brain, that they're trying to give some really kind of biological meaning to these things. No, for one thing, what thing I understand easily is why it's better than a graph. Why simplicial complex is better than a graph, because in a graph you're just saying, okay, this neuron and this neuron are connected, and this other neuron pair of neurons is not connected, right? And that's kind of yes and no thing. But with simplicial complex, of course, you can say, okay, we have this this part of the brain and this part of the brain, which is not elementary, right, already. And they are connected in this and that way. So it's much richer language. No, anyway, that's how looks effective, right? It works. And here we do have kind of abstract mathematical object as Vladimir wanted it, just to apply to raw data and compute it immediately. And that works without univalent foundations one against, right? So why still be serious about univalent foundations in this applied context? But here I have only very speculative argument. But still, I think that improve on relationship between pure mathematics and the application, this kind of fundamental level, it's not sufficient just invent a smart way to implement existing math on computer, right? So yeah, one really needs to rethink for foundations of mathematics, right? So probably set theoretic foundation are really not good in that sense, and of course they were not designed for that purpose, right? So the mainstream of people building mathematics on set theoretic foundation, what Marshall Stone told us, right? That was idea just to say, look, it's kind of abstract thing. We should disconnect mathematics from applications, from sciences, and that's what they did, by the way, right? So to fix it, we really need to go back to foundations, right? So one, it's not conclusive argument, but in low dimensions, really univalent foundations looks very intuitive, right? So they somehow reflect basic intuition about space and time. Here, MS means morning star and evening star, so it's very easy to solve this Frege's puzzle about how it's morning star can be the same star as the same object as evening star, right? Because we have this notion of continuous path or trajectory, which in that particular example kind of directly translates into homotopy type theory. No, but that's of course a kind of a baby example. It's not very, very serious. But anyway, we also, I think we don't have so many concurrent proposals, right? Because say, of course, it's an interesting question whether use or not use homotopy type theory with lean on another proof assistant. but it's not questions about foundations, right? So if we kind of formalize well in lean existing mathematics in this set theoretic form, there is no reason to think that it will be better applied to physics or whatever, right? And this topological data analysis is an interesting example. I think it's very, very interesting, but it's kind of isolated. So one probably would want to explore following Vladimir, this kind of global approach, right? Just change mathematics so it becomes more friendly for applications and for physics. So most part what I told is my paper in biosystem, which is also on archive. So thank you very much.
Thanks for the talk, Andrei. That's really, I found that very interesting and was not aware of a large part of that side of Voevodsky's research. So thanks.
Thank you.
Any questions from the audience? You can go ahead.
Should I stop sharing or I leave it for?
Whichever you prefer.
Mhm.
Okay, so I'll go ahead and ask a question. So, I mean, so a number of us here at the Topos Institute are engaged in the project of trying to use category theory as a tool for understanding scientific theories and models. And I'm wondering, so it's natural for me to wonder why Voevodsky, who knew, of course, all about category theory, was, at least in his early thinking on this, so focused on set theory as the foundational building piece. Do you know why that was?
I remember I actually asked Volodya about whether he kind of read the Laver stuff, right? Because I think I was very much, no, I'm not unlike him, working mathematician, and but apparently he actually didn't. Somehow he probably, of course, he had to know some category theory, right, for his field medal work. That's obvious, but I think he never really thought about that foundation or something. And when he began thinking about foundation, he, I don't know, take a book and discovered that it should be set something like that. But he was not very much in this movement. He might be unaware. And also we are talking about 2003, you see. So so that's rather early.
Thanks. I think I saw a hand raised. Lucas, I'm not sure if I'm pronouncing your name right, but go ahead and ask. Feel free to ask your question.
Excuse me, maybe me. Hello?
Yes, please go ahead.
So thank you very much. And I have such question to Professor Rodin. Namely, you have said that there is a proposition, as I understand from Voevodsky, to assume that not the mathematical logic, but set theory is considered as a foundations of mathematics. What is the reason of this? Because why not mathematical logic? More exactly, why not the functional calculus with identity, but set theory?
No, I think here it's kind of very standard view, right? It's something you can read in many books even today, right? About logic, he had later some ideas already within say Univalent Foundation. So he identified this propositional level, right? In this homotopical hierarchy, which actually he himself assigned number 2, but more typically in this hot book is number -1. So there it's sets are 0 level, and then you have -1 -2, and he just started from 0. But anyway, and so he identified this propositional types with the domain of logic. He said here it's where logic lives, but I don't think he was ever involved right in that theory. You have kind of a axiomatic theory without set axioms. So I think was for him something.
Okay, next question is about the Voevodsky's opinion about the crisis in mathematics. I read crisis in mathematics. I read about 10 years ago that during his lecture, he said about about the possible results of possible effect of inconsistency of mathematics. What about the reasons of the inconsistency of mathematics according to Voevodsky's opinion?
No, but that was a separate story. Okay, I did. And story was that when he already was appointed in Institute of Advanced Studies as a professor, right? It was, I think, and so he kind of came to this discipline of logic, foundational mathematics. That was very new for him. You see, even what we call univalent foundations, that thinks about homotopy, he developed more from geometrical point of view rather than from some logical foundation point of view, right? But then he tried to study that and give it to it. And so he gave this very provocative talk, according to which piano arithmetics was very likely. He didn't say it's proven or something. So he says we don't have proof of consistency, or even not only set theory, but also piano arithmetic, right? So it would be cool, really. It would turn out to be inconsistent. And he says that would mean that, I don't know, that all bridges fall down and it would be fine. Just interesting. Yeah, and that's actually people on this form list, if you know, like Harvey Friedman, they outrage because because that's true that Vladimir, no, maybe he used a little bit awkward expressions in his interpretation of Gödel's theorem, stuff like that. He was very new to that, you know, and open. But the community of foundations, it's reacted. And actually, I myself, I tried to defend him because, and finally, I kind of withdrawn myself from the list. Maybe it was a bit childish, but yeah. So I think he understood this reaction, right? And he didn't want to consider. So again, I'm not sure that it's best of his achievements. This who knows, but in any event, that's very separate. That shouldn't be confused with his project of univalent foundation. That completely different.
Yes. Thank you.
Valeria, did you want to ask a question?
Yeah. Hi, Andrei. Lovely talk. Very nice indeed.
Thank you.
I particularly like this idea of the 4 layers of mathematics, which I hadn't heard kind of before.
Yeah.
And, you know, it seems quite neat. That is something that Kolmogorov already was thinking about. But my question is much more about a different perspective on the whole thing. And I think some of your answer to the previous question is kind of perhaps explaining a little bit, because I think, you know, as traditional mathematicians, we think that we can conquer the world, right? That, you know, we can apply mathematics to all sorts of sciences and humanities and everything else. And that whenever we get there, then everything is going to be better because everything will be mathematical. But, and hence, I think lots of people like me tend to think that computer science is a huge field for application of mathematical ideas, that, you know, that what we need to have is more mathematization of computer science. And some of your discussion of what Voevodsky was saying is the other way around in some ways, right? Because, you know, in some ways, he's trying to say that computational thinking is as good as mathematical thinking. And, what we want, is just not to use our mathematical tools to think about computer science, but actually to kind of use the computational thinking that some other people have to make the connections between mathematical, pure maths and applied maths stronger, and to make the mathematicians more relevant in the world. So, I mean, have I got it wrong? Did you really kind of try to say a little bit about kind of that's the question. A bit.
Yeah.
What's the question?
No, my understanding is this. So first thing, that is kind of dogma, right? That he believed that really relationship between mathematics and the so-called real world is absolutely fundamental also for mathematics. So mathematics is not self-sustained somehow, right? So it's just a way to, right, that's one thing. Now, computer, in his view, is probably the only, but at least kind of evident channel between the two things, you see? So that would be a good question, whether all, communication between mathematics and this real world, using his word, or outside world, he called it, it goes from computer, or there are some other channels. That would be a good question. But I think he kind of was evidence, at least, that computer is really fundamental there, right? And hence this whole reasoning, right? So, but then it works in both directions. So in one sense, we implement our mathematics into computer. It's what you're stressing, right? We're using mathematics in computer science, and the computer, it's kind of transfers us further to, I don't know, physics or whatever empirical science. But very important for Vladimir was the opposite direction. So mathematics needs new problems, and he didn't believe that all good new problems could come from mathematics itself. Something
right, but there is another traditional thing. I think another very traditional thought that actually computer science is the physics of the 20th century, right? That physics developed mathematics in the 19th century, and that by now it is computer science that has this prototypical provider of problems for mathematics. So that is different from thinking that the computational intuitions are fundamental. But it's all it's a shame that we can't ask him more questions.
That's true. Too bad.
Thank you.
Thank you.
Thanks. So I'll go ahead and end the live stream here. So let's thank the speaker again.
Okay.
Thank you.